All right, folks, good morning. Let's start. Okay, today we'll study how stacks work. Runtime is like we're not talking about data structure stack that you use. Okay, we are talking about a runtime. Stack frames are formed when we make function call, and how do they work. So basic idea is about the principle, how does it work, and in x86 processor. And we have studied this in detail when we are studying RISC-V architecture. Okay, so this is just a revision from x86 perspective, and for those who have not done this course, MTech students need to be a little more attentive in the class, and please feel free to ask questions. Now this is very important because this gives structure. This structure gives scope for exploiting vulnerabilities. Okay, of course latest version of x86 have taken care of some of these issues. However, we can see we'll see it later that buffer overflow problem is maximally exploited bug. Okay, so we'll study buffer overflow problem little later. Today we'll try to understand how stack works. Once you understand it, then you have to write a code such that you can basically run a malicious code, okay, or any code that you want. All right, so before that, let's let's see where the contents have come from. So this, yeah, most of the contents have come from this book that's provided at the Berkeley site. If you just click on this link, you will get it. And then I have also used one diagram from this book, and another book you can see here is by Professor Wang Ling Du, and I think he is in Syracuse University. And this is very good book. It gives more of a hands-on approach, so we'll be using this book in this course as well. Okay, all right. So before we start, let's revise some concepts of OS, and we will not be doing OS security in general because most of the concept we have studied. Okay, so I will ask you a few questions to understand whether you have a good understanding of OS security. Okay, so this is the OS, right? Okay, all right, just a minute. Wow, something has popped in. Okay, all right, so this is the OS here, and then there on OS we run applications, right? The application right now we are running Zoom is running over OS. Okay, and there is hardware. In general, we cannot access hardware directly. When we say we, it means that any application here cannot directly access hardware. All right, it has to go through OS. For example, even you want to use printer, a printer server, or anything, mouse or keyboard or whatever, any application here cannot directly use it. All right, of course there are microkernels etc where some parts of the hardware can be used, but we are not discussing that right now. We assume that all access to hardware happens through OS. Okay, any doubt about it? No. All right, now the question I'm asking is that does the OS run on the processor all the time, assuming that there is single processor, not multi-core processor, just single processor, right? The question is that does OS run all the time on CPU? Anyone from senior batch, please tell me. No, because I have asked this question to you in quiz, so possibly you know it.
No.
Okay, yeah, very right. OS does not run on processor all the time, right? While most of us think that OS is running all the time, but OS doesn't run all the time. Okay, now the next question I'm asking is, yeah, you're right. Next question I'm asking is that, let's assume there is a malicious application here. And that has a control over hardware then, right? When it's running. When OS is not running, the application is running, then who protects, when this malicious application may want to do some malicious things? Who is going to protect malicious application at that time?
If any hardware access is requested, it has to go through OS.
Okay, excellent, very good. Okay, so basically when application is running, it's trying to access another application's memory area, or is trying to access a special function, privileged functions or privileged instructions, trying to execute privileged instructions, then immediately, now note that OS is not there at that point in time, that will cause an interrupt by hardware, because hardware is not absolutely passive device, right? It has intelligence, right? Okay, so the moment an app is a malicious app is trying to access or run a privilege instruction, or trying to do something, or maybe trying to use a device, then immediately OS will come into play, or the hardware will bring OS into action. Okay, this is how it is protected. Now I would request some of you who have no great understanding of this concept, please go through OS lectures. I have sent you the link. Okay, especially MTech students, those who have not done OS course. All right, so OS does not run on machine all the time. While most of us do think, because whole computer works at very fast speed, okay, very fast, so we get illusion that OS runs all the time. Okay, all right. Now next question is that who protects one application from another? When we say protection, means that one application is trying to access memory area of another application. Anyone?
Sir, kernel. Kernel.
Kernel, yeah. See, basically the concept of OS that we have studied in detail is based on, of course, kernel will come into play, is based on address space.
Virtualization of the memory and
yes, so virtualization is basically, virtualization is nothing but based on address space. You put different things, yeah. Virtual address space is same as you can implement it in any way. I mean, whether through page memory or it could be segment or whatever. Okay, so this concept is very important, and again I will request students to please go through it. Okay, so address space by itself, by design, when we say address space is between 0 to, if it's a 32-bit machine, 2 raised to 32 minus 1, virtual address is available to all, and process can play within that. Of course, a part of that is reserved for OS, but let's not worry about it. But so now is responsibility of OS to map the individual process of virtual address space into physical memory. And obviously OS will do it in a way such that there is a protection, right, in some sense, because they are mapped, different address space are mapped to a different physical area. And now if a process wants to access some other application's address space, okay, by design it cannot do it. right? Because it can only go to one of the addresses which is part of its own address space. All right. Any question? Because all applications will have what? Address space between 0 to say 2 raised power 32 minus 1. Okay, and each address space is mapped to different area. Like here, this address space for malicious app, this address space for address space mapped to this area, while address space for third application is mapped to this area. Okay, so there is automatically there's a protection. Okay, any question? Who does this mapping? And we have studied memory management, right? That's whole concept of memory management is exactly this. Okay. Now the question is that who protects OS from malicious apps?
Interrupts.
Yes. Basically, how can application? Okay, one is of course, I mean, if application tries to do access some part of OS, then hardware will recognize this, the processor will recognize it and create interrupt, and OS come into play and then do the policeman's role. Okay. But in general, there is a separation provided by something that we studied is this diagram, a dual mode of operation. Okay, it means that from user mode, it could be malicious application in user mode can go to kernel mode only through certain things like exception, interrupt, or syscalls. Now, interrupts cannot be done by user app. App cannot do and cause interrupt. It can cause, but it cannot say that now I'm interrupting. Okay. So it's generally through system call. Or exception could be because of some exceptional errors in execution by divide by 0 or something like that. Okay. So if malicious app tries to do something where divide by 0 result will be very big, so then there will be exception. The moment hardware sees that, it will raise an exception. Or the otherwise only way app can interact with kernel is through syscalls. So in some sense, OS is protected. All right. Or this is another view that this is the interface that this diagram we have also studied, right? Through system call interface, all apps can can interact with system. All right. And we remembered that what causes change of mode from user mode to kernel mode? It's just one mode bit, right? This is one of the status bit or flag, one of the flags is called mode bit. Or we in x86 we call it privileged bit. Who sets this privileged bit?
It is done in hardware.
Yeah, it is done in hardware. Very good. Because if applications are allowed to do that, then they can easily hack the machine. All the time, anybody can hack the machine, right? All right, good. All right. And then last thing that we have already studied, of course, there are a lot more in OS protection, but these are the main concepts, is the reference monitor that we already studied, right? Now, any subject, which could be a process, wants to access an object, which could be any hardware thing or any privileged thing, is given access. It has this request will go through reference monitor, is part of OS, and then this reference monitor will check the policy. For example, process with some process ID, say X wants to access hardware Y, it'll check the policy whether the process is allowed, because each process will have some access rights, which we'll study a little later. We read, write, execute. We have already studied this when we studied processes. We'll look at the details of the process, and based on the policy, it will allow or not allow, right? So this concept we have already studied. Okay, and apart from that, we have a concept of user ID, process ID, file permissions, access control, etc., which we'll study later. All right, so that's just think that these are the main things, and we'll study all this. Some of these you have already studied, like file and directory. What are the permission rights are there, but we'll revise it. Okay, all right. So that's a preamble. Okay, we'll continue to discuss this OS security a little later as well. So this is what we have studied in the last class. Remember, in create image in mind, process is different from program. There can be millions of exe files in your hard disk, if not million, 10,000s of exe files, executable files, right? But they are not processes. When these exe files are loaded in main memory, okay, a structure is formed. A structure looks something like this, something here, okay, which we call it memory image or process image, okay, and different fields are formed in that, and different data items are filled in right in the beginning, whatever is available, and then for local variables, etc., we use stack. So it's something like this for x86. We studied this in last class. We have code segment where machine instructions corresponding to the program goes. Data is where static variables, like global variables that don't change, go here, there, okay. All right. Then we have here stack. Stack corresponds to local variables. Like in program, you define various integer, floating point variable, or struct, or whatever. All those are created here. Okay. And then heap is that when we create dynamic memory, when we want dynamic memory, like through malloc, etc., right? So all the heap is created here, and the stack grows downwards and heap grows upwards. This is the highest address, and this is the lowest address. So stack grows in this direction where address top of the stack is at lower address than other elements in the stack. Okay. All right. So, all right. And then we have looked at the x86 register set. All right. Now let's start. For next 40 minutes, 35 minutes, we'll try to understand this concept. Now, note that as we, from main, we are calling a process or a function, a function, then corresponding frame is formed. Okay, that we know. All right. So a frame is formed. So basically, when we say frame is formed, it means that OS has to reserve some area or create some area or create some space. Okay, and this lifetime of this stack is as long as that function is in execution. When function execution completes, that area is released. Okay, so remember, if you do recursion, then until the loop ends, until the recursion ends, we'll keep on creating frame after frame of the same code set or same function. Okay, and as it gets over, then we keep removing those frames. Okay, so frame goes away when function returns. Now note that stack starts at higher address, and every time your code calls a function, stack makes extra space by growing down. This is very simple, right? All right. So now the way in a program you define various variable, you define struct and so on, and then process is making a function call, then you have arguments. There is a definitive way that's defined in which these values are stored. Okay, for example, string is stored from lowest address to highest address. Okay, note that if this is the stack, okay, this is higher address, this is lower address. So now string values will go this way. First value will go here and then so on, right? Okay. Now look at this is the main, for example, that has called a function. Okay, then corresponding to function, and when it's in execution, that function is execution, the frame corresponding from frame will be found, and this is the frame here. Okay, we'll get into details little later. Now note that something below this function that's in execution is free memory. If this function calls another function, then another stack will be formed and the values will be filled in. Is it clear? Is it okay?
Yes, sir.
Okay, right. Now there are two pointers here, EBP and ESP. Now note that E stands for extended one, right? I mean 32-bit machine, right? But and okay, and the x86 terminology is slightly different. Now when we say base pointer, it's actually at the base of the current stack frame, from where address is basically points to the address where the current stack that is in execution, it points to that address, right? So where the frame starts, current is frame, where the current frame starts. ESP is a stack pointer which always points to the top of the stack, right? So if there is a current stack, the ESP will point to the point here. All right, okay. Another question I am asking is that why do you need base pointer?
Sir, maybe to relocate PC.
To relocate PC, yeah.
For easy indexing for programmers.
Okay, programmers will not bother about EBP, right? Okay, all right. In some sense, you know, if you do assembly language program, of course, yes. See, what are you putting? You're putting local variables here, right? Inside. How do we access those local variables? It has to be referenced through some memory location. When you actually convert, when you know, suppose the value of some variable A is here. How do we access this? The B is here. Now we will say EBP value for the frame is fixed while ESP keeps changing. So we'll have to always reference these variables in relationship with EBP. So as we can say EBP B is 4 bytes away from EBP, something like that. Okay, that's the reason when we have to access, when machine accesses those, when it gets finally converted, suppose during execution of the function, of course something that's stored, local variable stored, will be used in the program. Okay, and value of whatever high level language, say ABC, etc., is converted into corresponding addresses. Now we are not going to use absolute address, but relative address here, right? Relative addressing that we are using. All right, remember this point. Okay, now pushing and popping, we already you would have, you understand it, right? Suppose we do this operation EAX equal to, so EAX has this value. This EAX is nothing but a register in x86. This contains the value here like dead beef. Okay, and we want to push this Okay, and when we say push EAX, now the contents will come here, which is there in EAX register, and ESP will change. Okay, to point to top of the stack, right? All right, and similarly we can do pop. Okay, when we do pop EAX, then this value whatever is there will go to EAX. So EAX will become this one, and then ESP will move here, and this memory becomes available now. Something that was here becomes available. Clear? Okay. All right. Now we'll have to now be careful in what order variables are stored in the stack. Okay. Okay, so local variables we know are allocated on stack on x86. And what happened in case of RISC-V? Because RISC-V, you can see now the advantage of RISC-V, because most of the variables, when are basically allocated on registers, because the number of registers were just too many in case of this kind of 32 registers, and out of which many of them were general purpose register, right? And most of the time in code that you write, only limited number of variables are into the play. So those variables are generally in the register. So access from register is faster, so it's more optimal. Okay. However, if number of variables just too many, so even in RISC architecture, we'll have to store those variables in a stack. Okay. Now, in case of 86, registers are not for storing local variables, but all local variables are stored on the stack. Okay. So individual variable in stack frame are stored with first variable at the highest address. Okay, and when we say highest address means what? We'll look at it, right? Highest is actually, I mean, again, look at this way. Highest is this way. So basically, if there are variable A, B, C, D, the first one will be stored here. The way, so you know, a function is defined local variable A, then local variable B. A will be stored here, then B and C and so on. While in case of stuck, you know, okay, in case of struct, first member is stored at lowest address. So it will go this way. You know, it has structure as 3 variables A, B, C. So A will go here, or we can say some other name, so X, Y, Z. The X will go here, Y will go at higher address, and Z will go further up. Okay, so this order is reverse. So global variables are stored with first variable at the lowest address. Okay, similar to struct. Okay, now let's look at the example. Okay, any question up to this point? Note that this is just a convention, and then x86 designer would have thought something why, well, some optimization etc. they would have done to see storing in this way helps. Okay. Question you can ask and you need to answer by yourself: how does OS know how much space to allocate for a struct? Allocating it downwards is always easy, right? Upwards, you have to have, you should know this, how much space you need. And for that, the answer is very simple. When you learn compiler, you will know. I mean, it's just not the most of the, you know, OS, most of the systems have multi-passes, right? So the OS knows exactly what is to be done. This information actually will be available in ELF file. Now look at this code. This is the main function, and it's calling a function. Oh, sorry, it's a function, and it's using a struct foo. and struct foo is defined here. Okay. It has long f1, basically 8-byte variable, then int f2 and int f3, which is 4 bytes each, right? Let's assume it's 4 byte, because, and again, different processor, if you take 16-bit processor, it could be value of int will be different. Okay, but let's assume that this is the way it is. Okay, so now let's see in what order variables will be stored on the stack. Okay, so execution starts from here. First is int a. Where will int a will go now? Okay, a will go here. What is next one? Actually, I should have. Okay, all right. Now here the second instruction will come into play now, right? So struct foo b. Okay, now how much space we need? We need this is 4 byte, 4 byte, 4 byte. So total we need, in order for foo we need 12, 16 bytes, right? So these 4 will be required. What will come here?
F1.
Okay, okay, all right. So 2 bytes of f1 will come here. Okay, all right. Yeah, and then f2 and f3. So that's it, is right. Simple. Any doubt? Because it's we studied little, yeah, here that struct are stored with first member at the lowest address. Okay, all right. Okay, now we'll again go into an example. So this one, this already we know, so we'll not okay, all right. So this simply says that the program counter, okay, all right. So when a function call, this is a main function caller, and it calls a function foo. This is foo. Okay, when foo is to be executed, then program counter, which we call instruction pointer in x86, goes to, is set to the first instruction of this. Okay, and when this execution is over, then control will come to the next instruction after foo in the main program. All right, that's all it says, right? Simple. All right, now let's look at an okay, so the same thing that we studied earlier. So now, so what we studied is up to now variables, and we studied struct, right? So this kind of convention is defined for many others. So what, and also we'll have to look at the arguments. When we are calling a function foo, then we may also pass some arguments to it, right? Here we have not shown anything, but here there can be some arguments, ABC, for example. Okay, it called foo ABC. Then what order this ABC will be stored? That's also defined, right? So when we call a function, say function the value 1, value 2, value 3, then we will place value 3, this one, at the highest memory address, then value 2, and then value 1. All right, and similar to RISC-V, the okay, this is in contrast to RISC-V, that wherein arguments are passed in registers. Okay, while in case of x86, arguments of a function are passed on to stack. Now, passing into stack is expensive. Any memory operation is expensive operation. That's the reason RISC is faster, because RISC does it through registers. And return values are passed in EAX here, which is similar to RISC-V. Okay, all right. And then we remember the concept of caller saved register, callee saved registers in architecture. Okay, and every architecture defines certain registers as caller saved. It means that before moving to a function, the calling function or the function that's making a call must store some registers, and those registers, because these registers can also be used freely by the callee. Okay, all right. So now when control comes back to the caller program, then these register values are restored. Where these registers will go to? They will go to stack. Similarly, there are some registers which are callee saved. So in case of x86, EAX, CX, and EAX, ECX, and EDX are caller saved, and remaining are callee saved. Now, please, I will request you to go through again. If you have forgotten caller saved, callee saved, please go through the lecture that we studied in an architecture course. Okay. So now what will happen when calling a function? Now note that when calling a function, then when function call is over, then control has to come back to the program that has called. So it means that now value of EBP and ESP have to restored. And when there is a function call, the value of EBP, a base pointer, and stack pointer has to be adjusted. All right. So now let's assume that this is the main program that's making a function call. So this is the value of EBP, which is starting of the frame, and ESP at the top of the frame. The stack pointer is at the top, and makes a function call. All right. So as a part of function call, this stack frame is added, which we call as callee frame. And then note that EBP always points at the base of the current frame. So EBP will shift from here to this place, and ESP will shift to something on top. All right. And once this is over, then again, when this function call is complete, then again value of EBP and ESP will be adjusted. Okay. All right. Any question? Simple. Okay. All right. Let's move. Now let's look at the steps on x86 function calls. First is that when there is a function call, let's say for example foo abc, first push the arguments on the stack. So these are the arguments abc into the stack, right? Now what's the next thing is push old EIP onto the stack. The PC here I pointed to. Now EIP again is Intel terminology is very confusing. Okay, EIP is nothing but program counter. Now from the main program you are making a function call, so we will have to come back when function call is over. So we'll have to save the value, right? So then we push the program counter value, which we call instruction pointer, to stack. Okay, so now this old value that has gone, or the before function call, okay, the value that's stored we call in Intel terminology as RIP, which is nothing but a return instruction pointer. You can use in your mind, because you have come with the background of RISC-V, you can still think the old PC value. Okay. All right. So what is the next thing that is to be done? The move EIP. Okay. EIP is nothing but program counter. The call is first instruction, right? Then basically, now note that while we are talking about stack things are coming here. Code is here at the bottom, right? Which is text portion or code portion, right? So here the move is, or instruction pointer always remains in this portion, or program counter. So change the program counter to callee's first instruction. Let's assume that this is callee's code, this caller code. So PC will now move from here to this place. Will come in next diagram, of course. Then push old EBP to the stack. We are adding, for example, another stack here corresponding to foo. Then change the we'll have to change this EBP or frame pointer from here to here. Then if we don't save it, then this value will be lost. So then we'll save this value of caller program, okay, or main program. Okay, so we'll say then push EBP into the stack. Okay, now again Intel uses a terminology called SPF, saved frame pointer. Okay, but you can think in your mind is old base pointer is to be saved. All right, then of course new stack is starting. Okay, so change the value of base pointer to the new one, fine. Okay, and similarly now ESP is still pointing to this one, so now change the ESP to something here. Execute the function. Once the execution of function is over, then change the value of program counter and EBP to previous one. That's it, simple. That's it. And then remove those arguments that we have pushed in corresponding to ABC from the stack. So these are the steps. Any doubt? No? Are you able to understand what's happening? Please go through this PPT and go through also the text that I've sent from the course, right? It's given to you. Just go through the entire text, you will understand the concept. Now let's look at example. This is a callee code. This is a caller code. Caller is, you think of main, and then callee is like foo or whatever, right? Okay. So this written in C, and we'll change this to assembly. It will look something like this here. Okay. All right. So now note that in a stack, sorry, note that in memory image or text position, we'll have always machine instructions available, right? And now for our convenience, we'll see instruction in red color, the one which is in execution. And EIP pointer is nothing but program counter which points to current instruction in execution. So we'll go now instruction by instruction and see what goes into the stack. All right. So now let's see how it works out, right? Right now EIP is here at this point. Okay, we are in the caller function. Okay, and this is a program. This is a program. So it says that void caller, so caller, and then callee with function values 1 and 2. Okay, so callee has two arguments A and B, which is corresponds to now here 1 and 2, and then it has local variable, and then it's simply returning value 42. So when we are here caller function, then first push two arguments in reverse order, right? So push 2 and then push 1. So it will come like, oh, okay. Okay, all right. Okay, all right. Let's see. Let's do. This is the caller stack frame, and then we'll have to now after this point we'll have to push these two, right? So right now EIP is here. So next thing is push 2. Okay, and then push 1 is in reverse order, right? Okay, now it comes to call callee. It means now there is a function call here. Okay, now before its control goes to callee, some more things are to be stored, right? And it will be nothing but return address or old program counter. Okay, so this actually this address here, because this is next instruction after this will be executed, will be in main or caller will be this one. So this will be the return address. So it will come in the stack here. Okay, now we come here to the callee function, right? Okay, in order to come to callee function, we'll have to what? We'll have to change the value of program counter. Okay, that is not shown here. Okay. Okay, all right. Okay, so now okay, so now when we execute any function, there are certain things we have to do a priori, right? That is push the old value of EBP or base pointer, because we'll have to go back to main program, right? Okay, and then what we'll have to do, we'll have to change the value of stack pointer. Okay, so it becomes like this. Okay, and then what we'll have to do, then we'll have to okay, then we come here, then okay, now we are returning 42 and return value will be in EAX, so we'll move 42 to EAX, right? Of course there will be nothing in its stack. Okay, and local is we have just created, so local comes here. That's it. Now execution of this function is over. Okay, now we'll have to change the value of ESP, EBP and program counter, which is nothing but instruction pointer, EIP. So these functions we'll have to do now, and the one with that shown are here, right? Okay, so next, all right, sorry. So next function is that change the value of EBP. Okay, stack point, change the value of stack pointer to EBP. So now move this stack pointer, because now this becomes this will go away, this will become free, so this will become ESP. Okay, and then we'll have to change the value of EBP to beginning of this one, right? Okay, so now this is the next thing that we'll do, and now of course we'll have to change this. Okay, okay, so and then we'll have to retrieve the value of function pointer or a saved frame pointer, which is nothing but EBP. Okay, so once we pop the EBP from here, then we get the new value of EBP, and then it starts pointing to the beginning. Okay, all right. Now next pop operation we'll do, we'll get return instruction. Basically, let it go to main program. So it will start when we pop this, then EIP value or PC value becomes this address. Okay, which is return address, right? Okay, so we'll have, in order to do that, we have to pop once more, which is not shown here because it's part of return instruction. Okay, and now value of stack pointer, because this all goes away, this also goes away, so stack pointer will point to this place. Okay, all right, and then of course, I mean, we'll have to, okay, then these two which are nothing but arguments corresponding to A and B, the one here, will also go away because function call is over. All right, just a minute. Yeah, so this is the final value. Now the execution will start in the main program, if there is something. Any question to this one? Are you able to understand how ESP, stack pointer and base pointer will change continuously? Now note that when execution is in a function and a frame is, a stack frame is created for that, EBP for that frame remains the same, only ESP changes. Only when the function execution is over, then value of EBP goes back to the previous one, and the value of that old EBP or base pointer comes from the, because it's saved in a stack, old value is saved in a stack. When we pops it, it will get the value of EBP. Okay, any question? So why are you studying all this? It's part of architecture, right? computer architecture. You need to understand two concepts of architecture and concepts of OS very well to understand the attacks. These two are needed. Okay, so now we know how stack works in x86. We'll have to find out where to attack then. Anybody? Out of all these things that we have done, where can we attack? Any guess?
So memory of a stack is full if
Yeah. Memory of a stack cannot be full. You'll have to keep going down. Yeah, that's a possibility that you keep going down and you hit on heap, right? But that's very unlikely. Because nowadays memory, is address space is huge. It was a problem long time back. 2 raised power 64 was such a big number, right?
We will use large move operations, means large addresses.
Yeah, but that is compilation error, right? In the beginning. Yeah, beyond this we cannot use, right? Because your instruction can be in the range. If you're, trying to jump into instruction, it can be always in this range 0 to 2 raised power 2 raised 62 minus 1 or 2 raised 32 minus 1. So, right, if you try to do right in the you will get compilation error or something. See, the place where we will play, and most of the vulnerabilities that have been exploited in the history is because of something that's here. So we are returning to a main program, right? If you override this old PC value program pointer, where you'll have to go back, and if you change this to a code that somewhere is there, okay, which is malicious code, and change this PC value, override this PC value to the starting address of this malicious code, then you are done. Okay, this is the maximally exploited hole in x86 architecture that has been exploited majorly. Of course, x86 has now become smarter, and then they have something called address space randomizer, etc., to such that it's very difficult to guess where this or return instruction pointer field is, right? If you randomize this field, then it's quite difficult, but nevertheless. So this is the one of the exploited hole. All right. So now that's all for the class today. So we have studied the x86 convention, and we have studied this primarily to understand how stack works and various local variables, then EIP instruction pointer are saved. And because now the all x86 all machine that are based on x86 will have same way of storing EIPs and base pointer, etc., etc. So this can now be exploited. Okay, all right. Thank you. Any question? Please go through slides, because if you have not, if you don't remember it from architecture course, then please go through slides all over again. Okay. All right. See you then on Wednesday.